Hello, this is Osman Doluca, and I'll be showing you how you can use Unity to simulate folding of DNA molecules today with a simple two-dimensional space. I hope this will show how versatile Unity can be to create simple simulations that can help us understand certain natural phenomena. And here I'll start with two game objects. One is the strand, and it can contain nucleotides, and we're going to start with the adenine nucleotide. We're going to be adding adenine nucleotides to a distant joint to keep the nucleotides attached to each other. It automatically adds a rigid body, and we're going to be adding a circuit collider, and we're going to be adding another script that we're going to manage our forces on the DNA. So we call it nucleotide controller. And we're going to be creating a folder for our prefabs and move that into this folder. So it's going to create an automatic prefab, and we're going to make all the changes on these prefabs from now on, so we don't have to keep it on this on the scene. Now we're going to be using strand controller as a means to automatically populate the strand with the necessary nucleotides. So we're going to be referencing to these prefabs, and we're going to have a sequence that is going to we're going to take the decide which nucleotides are supposed to be created. So we're going to be using a dictionary that's going to identify which prefab is going to be assigned depending on the type of the character in this sequence. So we're going to iterate through the sequence, and for each character we're going to decide whether or not which game object is going to be created, and that is going to be kept inside this denucleotide prefab dictionary, which is has A, C, D, G as the main keys. And here we're gonna use adenine. We're gonna make 4 copies, and then change the names to the 4 nucleotides, and we're gonna just choose different colors just to indicate. So blue timing, teal timing, no, blue timing for cytosine, will be more yellowish, and finally guanine. Now remember, we're just here to simulate how these forces that are going to affect on DNA is actually finding the folding of the DNA. So it's a random sequence. Now once as expected, once we run it, we have all game objects created. Next, what we're going to be doing is we're going to take the distant joints in each of the game objects. So we're gonna just find them at the beginning on start. We're gonna find the joints from all the game objects we have just created, and then we're going to attach them to each other. And the attachment is always going to be from the first one attached to the next one, and the next one, second one attached to the third one, and so on. Until the last one. We have to ignore the last one. That's why we use joints dot length -1. And once we run, we're going to see each of them has a connected rigid body and a connected rigid, so it's forming a chain. Except the last one is connected to, because it's connected to just empty space, just a certain point in space. Here is an example. We remove the gravity, and this is how they react without the gravity. Now what we're going to be doing next is we're going to be looking in these forces. And the first force we'll be looking at is phosphate-phosphate repulsion. So it's an electrostatic force that pushes the nucleotides away from each other, even within the same strand. This is the main force that keeps the DNA straight. So this force vector is principally equal to the constant times the charge of the phosphates divided by the distance square of the distance between the phosphates. Now in this case we're going to have it since the phosphates are the same, we're going to have k constant, an arbitrary constant, times the phosphate charge squared as a separate variable. We're going to write it that one down. Yeah, and then we're going to use that one to multiply the normalized vector between the phosphates, between the nucleotides, times delta time. And now we're going to be performing this force, applying this force for each of them. There you go. Now we have just have to pull apart, and there you go. We have everything, but the charge is zero. It's set to 0, so we're gonna increase the charge 1. As you can see, it started moving. They're trying to get away from each other as much as possible. So 10 seems to be a good value. So we can select all the prefabs and set to 10. This is could be an easy way to do this. We can set its constant, but for now we're just gonna use this one. So now we're gonna define a nucleotide type, because now we're interested in doing the second part, and what we have to define whether or not the two nucleotides are going to be matching, so that there can be Watson Crick hydrogen bonding forming. So that we have to have a dictionary to define which base pairs are going to be matching. So we're going to keep the information in the dictionary, and we're going to write down which nucleotide types are going to be forming this hydrogen bonding. Now to do that, we're going to define an enum, which is the nucleotide type, and we're going to have a dictionary defining which nucleotides are associated here. And we have to define two variables, the hydrogen bond distance limit squared. The squared is just because this is simpler for calculation to computer, and hydrogen bond force multiplier. Since these are arbitrary, we don't have to worry about what these start values are. We're gonna define them later. And now we're going to create a new function called apply Watson Crick attraction. Now to apply Watson Crick attraction, we have to make sure that first of all our nucleotide is matching to the other nucleotide. So we're going to use the Watson Crick base pairing dictionary to check if there is a match. And if there is a match with the other nucleotide, then we are going to be dealing with it. Next thing we want to do is that we want to make sure that the two nucleotides next to each other aren't forming these hydrogen bonds. To do that, we have to look at it through the connected body and attached body, that they don't have each other's connected, they didn't have assigned each other as their connected bodies, so that we won't be forming a hydrogen bonding between two nucleotides next to each other. Technically, it's not possible anyway, because they are sterically in not a suitable position. So if the distance between two nucleotides that meets these conditions should be able to form a hydrogen bonding, and we're going to be adding force if the hydrogen, the distance is the square magnitude distance is under the hydrogen distance limit squared that we will define. Now we're gonna define this arbitrary numbers again. We have to define each nucleotide as the prefab, and we're gonna start now. And we have these, as you can see, these lines, white lines, are indicating the formation of hydrogen bonds. Now we're gonna have to try something that we can form. We expect it to form something like a hairpin structure. So this should expect to form a hairpin structure, but it is more like a clump. Now that's basically because then more than one hydrogen bonding as Watson Crick base pairing is allowed to happen here. So we're going to make sure that we're going to have only one Watson Crick base pairing allowed in each for each nucleotide. So we're going to define an is base pairing variable that's going to control whether if this is already matched or not. So if it is not matched, then we're going to apply this. We're going to use this direction vector, and we're going to add the force to the opposite, the other nucleotide, and we're going to change the is pairing to true. Once we do that, the only thing we have to add that we have to make sure that is pairing is false in the late update, so we don't have to that it can be restarted calculating from scratch every update. Here we can see we can have some attraction, and arbitrarily we tried it. Is 26 seems to be forming hydrogen bonding as we expect. Set 26 for all of them, and we can try again. And as you can see, it's automatically, with a small nudge, it's automatically forming that what we expect it to. Then now it's better to put all everything that requires the other nucleotide in one place. So if there is no base pairing in the current nucleotide, then it considers for Watson Crick base pairing. And I'm trying to put some distance from the, with every nucleotide, we're going to try to put some distance away from each other so we don't have to worry about pulling them apart. So let's try again. We're going to put a sequence that is supposed to form a hairpin structure. There you go. It's forming a hairpin structure, and it does. We don't even have to pull anything. So if you put a random sequence, well, relatively random, we expect it to stay more in a linear form. It's made for some clumps. That's probably because we can play around with the hydrogen bond distance limit and even the force multipliers to make sure that we're not going to get gonna have less of a double strand in a random sequence, obviously. Now, can try 5, and well, it could work if we can just have a nudge and bring it together. Yeah. Okay. So in the next video, we'll be looking at the temperature effect and the effect of the magnesium ions. And thank you for watching. I hope this was interesting and helpful. Please comment below.